Hi, this is Professor Pradyot of Leadib Academy. We are looking into the question number 2, video solutions of IBDP Chemistry HL Paper 2 of May 2019. And I have provided the paper reference number. And Leadib Academy, we do provide the courses for subjects like chemistry, physics, maths. Okay. And you can always visit our website and have a look at those, okay, so that you will have a deeper understanding of the subjects. And besides this, okay, very interestingly, we are not only providing just the video solution, but we are explaining the underlying concepts, okay, so that you will have a deeper clarity. So let's begin. We are looking into the question number 2, okay. The thermal decomposition of dinitrogen monoxide occurs according to the equation. Okay, so equation has been provided. So let me write it down. Okay, the equation is like this. 2N2O, thermal decomposition, we provide heat. 2N2 gas plus O2 gas. Now, what do you see something interesting about this reaction? Clearly, there are 2 moles of the reactant, and basically in products, we are getting 2 moles plus 1 mole. So there's a clear cut, there is increase in number of moles, okay, during this reaction, because reactants are having only 2 moles while products are having 2 plus 1, 3 moles. Then we know very, very clearly that pressure, okay, is basically a function, okay, or it depends on number of moles. Why? That we have already aware of as per the kinetic theory of gases. Pressure of the gas, okay, because this is a gaseous reaction, okay, it is the number of particles which are colliding with the walls of the container in which we have kept the gas. So if there are higher number of particles, that means higher number of moles, the pressure is going to be higher because volume is almost fixed, okay, and we are not talking about the temperature here. So simple. So pressure depends on the number of moles, and in this reaction we are clearly seeing that there is increase in the number of moles from 2 to 3. So 2 moles to 3 moles. So clearly there is increase in number of moles by 50%. Okay, and therefore similar kind of a increase we can expect. So initial pressure is 200 units, okay, and 50% increase that will reach to 300 units. Simple. Okay, that's the reason. Okay, so everything, basically the important part is increase in the number of moles, okay, and pressure depends on the number of moles, or in short, number of particles. This is the underlying concept, very, very simple one. Okay, let's continue our discussion on the question number 2b, outline in terms of collision theory, how a decrease in pressure would affect the rate of reaction. Okay, so they are mentioning, so first of all, we are very clear Okay, the first thing, there is a direct relation. Pressure is directly proportional to number of moles. Okay, that we have seen. So if there is a decrease in pressure, okay, therefore decrease in pressure implies that there is decrease in number of moles, okay, for a given volume. So what does it mean? This means that n number of moles divided by volume is decreasing. What is N by V? Moles upon volume. That is nothing but implies concentration, okay, is decreasing. N by V, number of moles divided by volume. It means that in the given space, okay, so let's say this is the container, okay, the particles which are there, okay, their spacing is increasing, okay, they are going far apart. Earlier they were very close, now they are just going far apart, okay. So obviously now what is going to happen, that their collision frequency is also going to decrease, okay. Collision frequency, because of this decrease in concentration, it will means that frequency of collisions, okay, between molecules will decrease, okay, simple. And we know that rate of reaction, as per the collision theory, rate of reaction depends on frequency of collision, okay, obviously of reactant molecule, okay. So if the frequency is very high, frequency means how at every second or every minute how many molecules are colliding with each other. So if it drops, the rate of reaction will drop, okay. So therefore, okay, rate of reaction will decrease, simple, okay. So how we started, we first look into the pressure is means pressure depends on the number of moles or number of particles. So when we have been given decrease in pressure, it means the decrease in the number of moles for a given volume. Then in the given volume, if the number of moles or number of particles are decreasing, that means concentration of the gas is decreasing. And basically concentration is decreasing, that means the frequency of collision is going to drop, because now in the given space, okay, there are basically these molecules are far apart, so their frequency is going to take much, okay, it will not be very high. And because of that, as per the collision theory, okay, the rate of reaction depends on how fast, how quickly they are colliding with each other, because reaction occurs because of the collision. So faster the collision, faster the rate, simple, okay. So very, very straightforward. Okay, let's look into the next question. 2C, decomposition obeys this rate expression. This is in the differential form. Okay, let's see. So it is given like this: minus d N2O dt is equal to K N2O. What does it mean? It means, okay, this negative sign, if you recollect, this means that the rate of reaction, okay, that is basically dropping. The reason being that reactant is getting converted into product as the time progresses. So the concentration of reactant is obviously dropping because more and more reactants are getting converted into the products. Okay, so the rate of reaction is dropping. Okay, and that's the reason that minus sign. So obviously after time t is equal to 2, okay, the rate of reaction has to fall. Simple. Okay, so I'll say as time progresses, more reactant molecules, so to be very precise, N2O are being converted or getting converted into the products. Therefore, concentration of N2O decreases as reaction progresses. Okay, so therefore at t is equal to 2, rate of reaction will decrease. Why? Because this is going to drop. Okay, this is getting reduced, so the rate of reaction has to drop. Okay, that's the reason. Simple. Because N2O concentration keeps on getting reduced. Simple. Okay, so it is very, very simple. Okay, and that is how we define the rate of reaction also. Okay, so the question number 2C, 2C2. It has been suggested the reaction occurs as a two-step process. N2O giving N2 plus O, and then N2O plus O giving you N2 plus O2. Okay, so let's see how it is going to help us. So let's see. N2O giving N2 plus O, nascent oxygen, and then N2O plus O giving N2 plus O2. So this is the first step, second step. Now let's add both this. So what we'll get? 2 N2O giving us, sorry, okay, let me make a mistake. Okay, fine. 2 N2O plus O giving you 2 N2 plus O plus O2, and let me cancel something which is common. So obviously this nascent oxygen, that means it was intermediate product. Okay, so what is left now is this. So it is very much confirms our reaction. Okay, now please get the focus on this rate expression. Sorry, this rate expression. D of N2O dt minus is equal to K into it N2O. Now, if you observe very clearly that there is only one molecule which is its concentration is playing a role or it is impacting the rate of reaction. There is only N2O. Okay. So if you observe very carefully, in the second step, there are two reactants, that is N2O and oxygen also. While in the first step, there is only N2O alone. So it clearly and okay, we can clearly imply that means the first step is the RDS. That is the rate determining step. Okay, it clearly states that is first step. Okay, that is the RDS which determines the step. That means it has to be a slow step. Very, very simple. Why? Because from the rate expression, there is only one molecule, that is N2O, okay, that is a reactant which is getting involved. And in the second step, there are N2O plus the nascent oxygen. In this case, there is, okay, so there is no nascent oxygen which is getting involved as per the rate expression. So clearly, okay, so it is very clear that the first step has to be RDS, okay. So it is very, very simple one. And basically we can conclude that this is nothing but first order reaction and unimolecular. First order, the reason being that the power is 1, okay? And only N2O concentration is playing a role, even though it is a two-step mechanism, but only the first step is playing a role. So that means the second step is a fast. Okay, very, very straightforward. Okay, let's look into the question number 2D. The experiment is repeated using the same amount of dinitrogen monoxide in the same apparatus, but at a lower temperature. Okay, so the number of moles or amount is same. Okay, the volume is same, only it is being carried out at the lower temperature. Now, we people are aware of that pressure is the function of temperature. That means there is a direct relationship. Okay, pressure is directly proportional to the absolute temperature. So if we lower this temperature, pressure will get reduced. Okay, so as we lower T, okay, P will also get lowered. Okay, that is one concept. So therefore initial, so let me try to draw on this graph. So when we say the lower pressure, so let's start with this. Okay, I'm just taking arbitrary. Then what else? Okay, so the initial pressure as well as the final pressure is going to get lowered. Okay, and then what about the initial gradient? Okay, so the gradient, okay, because that is the initial rate. So please understand, for the given graph, okay, it is like this. This is going to be the initial rate tangent. So this has to be much flatter. Okay, so let me try to show how it may look like. Okay, so this is how it will look like. So what we can say, initial pressure as well as final pressure will be lower, and initial rate also will be lower. Okay, because we are already proved that pressure and initial rate, there is a direct correlation. Okay, it directly depends on the pressure, so we can conclude that. Okay, so let me remove this I had just shown. So this kind of a graph we can expect, okay, which will be lower. Okay, it is never going to be something like this. Okay, hope this is quite clear to you. Okay, let's look into the next part of the question 2E. So the same experiment, and now they are mentioning that the experiment gave an error in the rate because the pressure gauge was inaccurate. Outline whether repeating the experiment using the same apparatus and averaging the results would reduce the error. So what kind of error? Okay, so basically this pressure gauge, okay, the pressure gauge, which is an instrument for measuring the pressure, okay, it may look like this. Okay, I'm saying analog like this. Okay, there would be, and then it just turns around, okay, depending on the pressure, and you fit on the container, okay, for which you need to measure the pressure. Okay, so now if this is faulty, okay, that means this is a systematic error. Systematic error. So how we can eliminate this? By proper calibration. Okay, whatever is this one. But if you repeat this experiment, the same error is going to keep on getting ready. Okay, it will keep on occurring. The same kind of error. Okay, let's say there is a zero error, it will keep on happening. Okay? Or if there is some other problem in the calibration, it will keep on happening. So just by increasing the number of observations, repeating the experiment will not reduce. Okay. Hence, we can say systematic error by repeating experiment or by repeating experiments or observation will not reduce the error. Okay, simple. If it would have been a random error, yes. Okay, so in this case, since it is a systematic error, there is basically a problem in that measuring instrument itself. We cannot. If it would have been, there is an error like a random error because of the someone is measuring and those people are not measuring it accurately, then yes, then that experiment can be performed maybe 10-15 times so that error can be eliminated. But in this case, that instrument itself is faulty. We cannot, okay, minimize that error or eliminate that error by having performing the experiment number of times. Okay, very straightforward. Hope this is quite clear. Okay, let's see the question number 2F. Okay, the graph below shows the Maxwell-Boltzmann distribution of molecular energies at a particular temperature. Now the question is being asked, the rate at which the dinitrogen monoxide decomposes is significantly increased by metal oxide catalysts. Annotate and use the graph to outline why a catalyst has this effect. Okay, first of all, the concept should be clear. Maxwell-Boltzmann distribution, what it indicates. Okay, this graph is indicating, okay, how basically the different molecules, okay, or what percentage or what fraction of molecules are possessing kinetic energy, okay. And we know that higher the kinetic energy, okay, or the molecules which are possessing higher amount of kinetic energy, they are going to have a successful collision because they are more energetic. Simple. To have a successful collision, the molecule need to have minimum certain energy, okay, minimum kinetic energy or minimum energy, and that is what we call activation energy, okay. And this Maxwell distribution is indicating how that energy is spread across those number of molecules, okay. So let's say this is basically the original activation energy, okay. So I will say this is EA, okay. It simply means that these are the number of molecules, or these fraction of molecules, they are only going to contribute, okay. So I'll say number of molecules contributing to the reaction, okay. Only this fraction is helping, okay. Let's say at a given temperature, and obviously this is without catalyst. This is without catalyst. Assume that, okay, this is the activation energy, that means minimum energy. So obviously the molecules must possess at least activation or higher. Now let's say we introduce the catalyst. So what catalyst does, we are very much aware of that catalyst, okay, takes the path, reaction path, which will have a lower activation energy. So obviously it means that new activation energy may be like this, okay. This I'll call it as EA with catalyst. So what has happened now? So we are introducing now these additional molecules, okay. I have whatever I have shown in this blue color. So I'll say these are additional molecules possessing energy greater than or equal to that EA new or EA with catalyst. Simple. So obviously if we are getting extra number of molecules which are possessing now the energy which is higher than activation energy, equal or higher, then obviously the rate of reaction has to be higher, okay. So that is how the catalyst helps. Catalyst basically reduces the activation energy, or it chooses the path, reaction path, which is having a lower activation energy than the original, because of which the higher number of molecules now are going to possess this kinetic energy or energy which is higher than activation energy. So obviously the rate of reaction has to be higher. Simple, okay. So that's why this Maxwell-Boltzmann distribution curve really gives a very good idea, okay, how catalyst works. Very powerful idea. If you are interested in knowing more details, so please subscribe to our courses, because we at Leadib Academy are providing these courses for chemistry, physics, maths, etc. Okay, so please do visit our website where you will find these courses. So let's see the next question. Okay, next question 2G1. Determine the standard entropy change in joules per Kelvin for the decomposition of dimethyl nitrogen monoxide. Okay, and we have been given the standard entropy corresponding to these compounds. Okay, so very, very simple concept. So what we have been asked to calculate this, okay, for the reaction. So we'll use this simple formula, that delta S naught for the products minus summation of reactants. Okay, sigma means basically the summation, that means whatever the products. So let's try to find out. In this case we are having, okay, 2 nitrogens. So let's see, for the nitrogen it is 193. So we will take it like 2 multiplied by 193. This is pertaining to the nitrogen, okay, and plus oxygen. Okay, so oxygen, it is only 1, so that is 205. And then we are going to subtract for N2O, that is 2 into 220. Okay, so let's do this calculation and you will get plus 151 joules per Kelvin. This is the entropy change. Very, very simple. Okay, the concept is summation of the product's entropy minus summation of reactant entropy. That is basically, okay, what we need to calculate. Simple, extremely simple. Okay, interesting question. 2G2 dinitrogen monoxide has a positive standard enthalpy of formation. Okay, deduce giving reasons whether altering the temperature would change the spontaneity of decomposition reaction. So first, let's break down. First of all, we have been given that dinitrogen monoxide has a positive standard enthalpy formation. So dinitrogen monoxide. So first, let's write it down, N2O. Okay, so N2O is obviously going to be formed from nitrogen and oxygen. Okay, so straight, so let's be clear that it is half. Okay, so these are the standard states. Okay, and now what we have been given, that delta HF naught is greater than 0, positive. Okay, very, very simple. So what we can conclude now? Okay, so therefore obviously we can now, instead of half O2, we can say twice N2, whatever is desired, make it, okay, remove the fraction, okay, and mention 2 N2O. Okay, 2 N2O gas. Okay, so again this delta HF will be obviously positive. Okay, very, very straightforward. Okay, so it means now if we reverse this reaction, because they are asking about the decomposition reaction, so we need to reverse this. So 2N2O gaseous twice N2 plus O2. Obviously now this, okay, this reaction delta H naught will change the sign. Okay, obviously this is very, very straightforward. Okay, if you reverse the reaction, the enthalpy, okay, changes the sign. So we are very clear now for this reaction. It is given that delta H, okay, for this reaction, okay, that is decomposition, is negative. Okay, it means simple that it's the exothermic. Okay, this is given. So now let's look into it. Now they are asking whether it is the formation. Okay, now whether they are asking whether it is going to be spontaneous. So which concept should come into our mind? Simple. Okay, now let's see. This is our focus. This information we have already received. Now for spontaneity, we know the very most important powerful tool, that is this Gibbs free energy. Okay, T delta S naught. That is delta G is equal to delta H minus T delta S. Now what is important or what is interesting one? Okay, now understand in this case delta H naught has already we have seen that it is negative. Okay, so please understand this part is already we have proved that it is negative. And what about delta S for this reaction? We can clearly see that delta S is positive because getting decomposed, here there are 2 moles, okay, and those 2 moles are increasing to 2 moles plus 1 mole, that is 3 moles. We have already seen that. That means since there is an increase in the number of particles, that means randomness is increasing, that means this has to be positive. Okay, delta S. Now you can see that there is some negative number minus and temperature. Please remember that temperature has to be always positive. There is no question on that because temperature cannot be negative because that is the absolute temperature, Kelvin temperature. Okay. So obviously this means that you take any kind of a temperature value, okay, any temperature value, the overall delta G naught will be always negative. Delta G naught will always be less than 0 for all values of T. So what does it mean? It means reaction is spontaneous at all T. So very important. Okay, delta H naught is negative, delta S naught is positive, and temperature has to be always the positive. So if we look into it mathematically, it's very simple. Delta G will always be negative, and we know if Gibbs free energy is negative, that means the reaction is spontaneous. Okay, very simple, very conceptual, very good quality question. Okay, hope it is very clear to you. Okay, and please do visit our website leadibacademy.com if you are interested in subscribing to our course, because we are covering all these concepts in detail like spontaneity, Gibbs free energy, enthalpy, okay, everything about energetics or rest of the topics from the chemistry.